Okay, so we've been discussing biophysical modeling of the four components of neural signaling. The first was genetic propagation, and second was action potential generation, which we already discussed. That's the Hodgson-Huxley model. The third is axonal propagation. That is, how does the signal, the action potential, propagate down the axon without losing its amplitude and duration. So we began with the Hodgson-Huxley model, which tells you how to generate the action potential. The thing is, it's a point. The HH model is a point neuron model, or you can say it's an isopotential model, in the sense that uh, so we have taken a patch of the neural membrane, right, and we have all these ion channels. So we assume that the potential is same everywhere, right? Vm of t is same everywhere, so no dependency on x, right? So that is the isopotential assumption. So therefore, it's a point neuron. Whereas now, if you want to understand how the action potential propagates down the axon, you need to have Vm as a defined as a function of both space and time. So how do you make this change? So the basic idea is that if you take your circuit model of the cable, right, where you have these RAs and at various nodes you have current going down, okay, with capacitor and everything. So this is your IM, right? So basically, the difference between current going in and current going out along the cable gives you the IM. So basically, some kind of if you take this difference, you can think of it as being related to the spatial derivative, right, of Vm. We'll show that we've actually shown that before when we derived the cable equation. So basically, a spatial derivative or derivatives can be linked to the membrane current Im. So this is how you basically come up with a equation for describing the axon propagation. So we need to introduce. So we need to basically write down the cable equation for the axon. What we have done before is cable equation for the dendrite, right? So we need to do it for the axon, which means we need to combine the Hodgson-Huxley model with the cable equation. So that's the challenge. How do we do that? We have the cable equation basically has a central result, which relates the second derivative of the potential with space with the membrane current. That's shown as equation 1 here. So we already derived this and then we derived the cable equation. Now the Hodgson-Huxley model is given here, right? The equation 2, which tells you how the voltage varies as a function of all the ion channel kinetics at a given point. So there is no space here. So like I said here, the spatial derivative right here must be related to the IM. So IM here in the passive cable, IM is simply the combination of the current through this passive resistance, ohmic resistance, and the capacitance. Whereas same thing in case of Hodgson-Huxley model will have, right, you'll have your RAs like this, but in addition you have all the three branches. And the capacitive branch. So this is the sodium. So this is the sodium branch, potassium branch, leakage, right, branch, and the capacitance. So this is the Hodgson-Huxley model. Basically, you need to connect this to the cable. So then you will have a model for axon propagation. So how do you do that connection? So the main thing is, the main insight here is the current that you describe in the Hodgson-Huxley model is actually membrane current. So all the currents that you see on the left side of the equation, that is the capacitive current, sodium, potassium, leakage, they all represent the total, that membrane current going out of the membrane. whereas membrane current in equation 1 is related to the second derivative, dou square Vm by dou x square. So you need to combine these two. But you cannot directly equate one with the other, because the problem is in the Hodgson-Huxley model, all the the currents are defined in terms of per unit length. So in the cable equation, sorry, in equation 1. Right, whereas in Hodgson-Huxley model, all the currents are defined as in terms of per unit area, right? Because we made the isopotential assumption and all that. So now, how can you convert? You need to convert the kind of the unit length currents into unit area currents, and then insert this term, the special derivative term, into the Hodgson-Huxley equation. So how do we do that? Let us see that. We need to bring this here by making a proper transformation, by expressing the current in terms of per unit area, right? Whereas originally this current in equation 1 is represented per unit length. How do we do that? So to describe propagation along cable, we need to express all the membrane currents as per unit length. That's what we have done before. Therefore, the small array is given by capital array by A. Right, we have done all this stuff. So array capital array by pi d square by 4 is equal to 4 array by pi d square. We have done this before. Now, for a given cable of diameter d, the membrane current per unit area of the axon is expressed by dividing the current in the equation 1, that is this current, by pi d. How is that? If you look at this simple schematic, Im is the current passing through the entire cylindrical strip of diameter d and width 1. So imagine this is a cylindrical strip of diameter d and width 1. Im represents a current going through this entire strip. Whereas what we want is current going through a small unit area patch. So how do we do that? Simply divide this Im by pi d into 1, which is pi d. So then you get current flowing through this small patch of unit area. So that's what we do here. So basically take Im divided by pi d. If we do that, then we get Ix, which is per unit area current, right? So we do that. We take this first equation, divide both sides by pi d. You get 1 by pi d Ra is equal to times dou square Vm by dou x square is equal to Im by pi d, right? So pi d Ra is given by the previous equation, that is 4 capital Ra by pi d square. So if you plug it in here, if you plug in here, you get d by 4 capital Ra times dou square Vm by dou x square is equal to Im by pi d. Okay, so basically, right, you take that and insert it into the Hodgson-Huxley equation. So now Hodgson-Huxley equation, which is originally a kind of point neuron model, now we have a spatial derivative here, right? And that becomes, it now becomes a PD. So actually this should be dou Vm by dou t. So because it becomes a PD. So now let us look for wave equations. The thing is, the original cable equation is also PD, but the equation is such that you won't have wave solutions. We did a lot of gimmicks and did some tricks to show that there is some kind of a propagating wave, right? This is something called some kind of a pseudo wave propagating along the dendrite. We have done all that before. Whereas in this case also, it's not obvious how you get a wave. You got to get a propagating wave in the axon, but physically, experimentally, we know that there is a wave, right? So actually, there must be a omega term here. Sorry, no, should be T is not subscript; it's ut. So we need to look for a solution of the type v of x minus ut. U is a velocity. Right, uniform velocity, and there is such a solution which is found experimentally. Now, if there is such a solution, then v of x minus ut, there must be a solution of this kind. Right, if there is a wave, propagating wave, which is found experimentally. Now, the PD for which this is a solution, the v of x minus ut is a solution, is given here, equation 5. Because this is a kind of equation we have studied. You have studied in your earlier classes where you derived the equations for sound propagation or the automatic wave propagation in Maxwell equations. But you might have done some of that in your earlier classes. So, so because there is a wave propagating wave, you should have an equation of this form, V of x minus ut. And if you have V of x minus ut as a solution, the corresponding equation for which this is a solution will be of this kind. That is dou square Vm by dou x square is equal to 1 by u square, u is the velocity, times dou v square by dou t square. So now you plug this result back into the first equation, right, into rather the equation number 3 here. Then what you have is 1 by k, where k is some constant, because if you substitute 5 in whether 3 or 4, then what happens is you can get rid of the spatial derivative, which you are now replacing with a temporal derivative, right? So then you have an equation of this kind. Left side you have dou square Vm by dou t square, right side you have dou v by dou t, because you have this. Since now v is dependent only on one variable because we got rid of the spatial variation, right? Then I can just use only ordinary derivatives, not partial derivatives. So d square becomes d square Vm by dt square on the left side, and on the right side you have just dv by dt. Now this dv by dt term comes from the dou v by dou t term, which is a capacitive part of the capacitive current. The second term, I ionic by Cm, this is basically the sum of all the ionic currents. Right, this whole thing is I ionic. Right. So you can easily verify that equation 4 after the substitution of equation 5 will be of this form. And once you make this, I'm replacing the partial derivatives with the regular derivative, dv by dt. Where this constant k, it turns out if you do the algebra right, you get it is equal to 4 capital R u square by u square Cm, capital Cm by d. Now, the fact that the constant k is of this form has an interesting consequence. Let us see what that is in a minute. Now, notice that all the currents expressed are in terms of per unit area. So that's what we have done to move the cable current Im, the membrane current Im into the Orson-Weasley equation. So therefore, since the currents are in terms of per unit area, they are independent of the axon diameter. So I don't care how big the cable is, since I'm only looking at current going through a small patch of that membrane, right? So similarly, voltage Vm is also defined at a given point on the membrane sheet. So that's also not dependent on the diameter of the cable. If I'm defining things in terms of the cable length alone, right, then diameter becomes a background parameter. So everything depends on diameter. But now I'm expressing all the quantities in terms of per unit area. I don't care what the diameter is. So therefore, k is the only quantity which is kind of a stranger here in this equation. I understand what is Vm is defined at a given point. So there's no diameter dependence. Cm also is dependent on per unit area. All the ionic currents, I ionic, are all dependent on per unit area because that's how I represented now. The only stranger here is k. So therefore, I cannot have all the quantities independent of d, whereas only one quantity is dependent on d. That's not possible. Therefore, k also must be independent of d. If k is independent of, but k has d as a parameter. So how can k be independent of d? And now let us now eliminate the possibilities one by one. R capital I is independent of diameter because you have taken this intrinsic quantity Ri and computed this diameter dependent quantity, which is small r. Okay, so therefore that's how you get this formula. But capital R is diameter independent. Capital Cm is also diameter independent. So you are left with only two quantities, u square and d. So we have concluded that k is diameter independent. Now d obviously is diameter dependent. The only quantity which is now questionable is u square. So therefore, since Ri is independent, Cm is independent, k is independent, u square by d also must be independent of diameter, which means u square must be proportional to d. Only then you'll have a cancellation of d from inside u square. So therefore, U square is proportional to d, or U is proportional to root d. That means the propagating velocity along the axon must be proportional to the square root of diameter. So note that it is very interesting that even here, so we have got a similar result even for in the case of the passive cable, where we defined the velocity in a slightly contrived fashion, and concluded that that kind of propagating velocity is proportional to the square root of diameter. So whereas in case of dendrite there is no real propagating wave, only in a very contrived restricted sense there is a propagating wave. Whereas in case of axon there is no problem. There is actually propagating wave which is experimentally observed, right? And so although the equation doesn't show that, right, since experimentally it is there, we made this other assumption and derived this property of k, and from that we got that U is proportional to square root of d. So here also there is the conduction velocity is dependent on only square root of d. So therefore, if you want to increase conduction velocity in the neuronal cables by increasing diameter, that's slightly expensive, because if you want to increase velocity by 2 times, you have to increase diameter by 4 times. That will increase the volume of the cable by 8 times, like d square, right? So it's a very expensive way. So what the nature has done, like I said last time, is to use axons, right? But with a composite structure. So instead of just a plain cable, nature has slapped on extra sheet, the myelin sheet, right? Because of this, uh, there's increased conduction velocity. For the same cable, right? If you add extra myelin sheet, it will have higher velocity, conduction velocity. And not only that, in this case, so this is myelin sheath. So in this case, U is proportional to D. Okay, so it grows faster. Uh, the conduction velocity grows faster with diameter. So this is a special property of myelinated axons. So therefore, if you look at the types of axons, there are large myelinated axons, there are small myelinated axons, and then there are myelinated axons. So large myelinated ones have highest velocity. Small myelinated ones have slightly lesser velocity, and unmyelinated axons have the smallest velocity. Now, if you simulate these equations which you have derived here, right, once you substitute this one, so equation 3 basically, simulate equation 3, right, and also you need to have an extra I inject kind of term here, right? So if you do that, then what you will find is you'll find a propagating wave, and here also there's a threshold effect. So that means, so if I take this axon, inject current somewhere, right, and if the current injected is, so just like in case of the Hodgson-Extreme model. So you have seen in your assignment probably that only when your injected current is more than a threshold, you will be able to find, you will be able to generate action potentials in the HH model. So similarly, even for axon propagation, only when the input current is more than a threshold, you will be able to produce an action potential which is propagating. So also one more thing here is, if you take an infinite axon and simulate it in the middle, obviously without loss of generality, due to reasons of symmetry, the action potential generated here will propagate in both directions. Okay, so then you might ask a question: how come in a real neuron we always say that action potential propagates only from the axon hillock to the axon collaterals? Well, that answer is easy, because this is a soma, this is the axon, right? So the action potential is generated in the axon hillock. Thing is, it could have propagated backwards also, but point is here this world is all passive. The dendritic tree is mostly passive. Here and there you might have a few voltage sensitive channels, but mostly it is passive. So even if it propagates a little bit, these waves will die quickly. Whereas the part of it which propagates along the axon outwards to the axon collaterals, right? These are, so you have voltage sensitive channels all along the length of the axon. So therefore, this wave, right, marches on without any loss. Okay, whereas whatever is tries to march backwards, right, quickly dies out. And having said that, let me also say that in some neurons on the genetic side also there's slightly more voltage sensitive channels. So in such neurons, you have something called back propagating action potential. So it's possible in some neurons. Okay, but so this course is mostly about principles. So I don't want to memorize which kind of neurons have how many and what kind of ion channels which are voltage dependent and present on the genetic side and all that. I don't want to mug up things like that. But in general, the genetic side is passive, so these waves cannot propagate very far backwards. Therefore, these only propagate forwards. So now, when you inject some current, right, the current goes not only at this point, it also, right, kind of diffuses a little bit to the neighboring regions, and that is called the local circuit current. I mean, in biology, we like to give names for everything, so I guess that's the name given. So when the input current is more than some threshold, it spreads. Now, when the current is close to a threshold but hasn't crossed the threshold, it's within just 1% less than threshold current. Then what happens is there may not be a propagating wave, but a decaying wave that dies down to the resting potential with increasing distance from the point of injection. So if this is the point of injection, I give a current which is close to threshold but not yet at the threshold, very close to like 10%, 1%. So then what will happen? It will produce something like that, and very quickly these waves die. You won't have a nice propagating wave which you normally expect in an axon. So thing is, so there is a threshold effect as far as injected current is concerned. There is also a threshold property as far as the strength of the sodium potassium channels is concerned. That means we have done this experiment even in case of Hodgkin model, right? So the conditions under which HS model produces action potential. One of the first conditions is that the input current must cross the threshold, and secondly, even the sodium potassium channels must be having sufficient magnitude. Right, that means there must be sufficient density of these channels in the membrane for the membrane to produce action potentials. So therefore, to this experiment, people have multiplied a factor h, a scaling factor, and multiplied both GNA and GK with that. So obviously, when h is equal to 1, the axon produces propagating action potentials, which we know. But then these guys in the paper, Cooley and Dodge, they reduced h gradually and found that when h is reduced to less than 0.26, action potential was generated, but it did not propagate as a stable wave, right? Only decaying wave was observed. So the thing is, when h is small, which means there are not many voltage sensitive channels. So in this case, even when the current is sufficiently strong, is beyond threshold and all that, they could not observe an action potential in the simulation, which is understandable because you need a sufficient density of GNA and GK for there to be an action potential. Okay, so that is some basics of, skip this, basics of axon propagation. Now we still have some time. Let me quickly cover a little bit about the last component, which is neurotransmission. Right? How do you model the synapse? So in the synapse, we know that you have the action potential arriving at the presynaptic terminal, right? And there it triggers release of neurotransmitter, and neurotransmitter is released into the synaptic cleft, and here it diffuses through this cleft and reaches the postsynaptic terminal. And there on the postsynaptic side, right? So these neurotransmitter molecules, which you see here, bind with receptor on the postsynaptic side, then that binding event of the neurotransmitter and the receptor acts on a channel, ion channel, and opens it, and because of that, current flows into the postsynaptic side, and because of that, you have a PSP, right? And if the synapse is excitatory, then the PSP is positive, so you call this EPSP or excitatory postsynaptic potential. And if the synapse is inhibitory, then on the other side, you basically either open potassium channels or chloride channels, right? That will reduce the voltage on the postsynaptic side. So as a result, you have IPSP or inhibitory postsynaptic potential. So we know all this from before. Now, one more concept which we need to know when we talk about neurotransmission is this concept of synaptic strength. That means when the action potential is, it arrives at the presynaptic terminal, right? We said there is a PSP produced on the postsynaptic side, either IPSP or EPSP. Now, unlike the action potential, which has a standard shape and size, right? The PSP is not like that. It is more graded. That means it can take many values. So it can take many values in terms of amplitude. It can also be positive or negative. And we also know that you can have some, this kind of temporal summation where PSP due to multiple action potentials adds up to produce a large wave. Okay, so we have all seen all this. Now, at a given synapse, if the PSP produces a small amplitude PSP, then you say that the synapse is a weak synapse. It's not able to produce much response on the postsynaptic side, right? So that is for a given action potential, right? A single action potential, a given synapse, it produces a small PSP, then you say it's a weak synapse. Similarly, for a given action potential, a given synapse, if it produces a large PSP, then you call it a strong synapse. Now, so you can think of, you can define something called a synaptic strain as the average PSP produced in response to an AP on the presynaptic side. This is a very important quantity because this quantity is not a fixed quantity, it's not a fixed property of the synapse. It can so happen that based on the ongoing activity over the synapse, a weak synapse can become stronger or the strong synapse can become weaker, right? So the strength of the synapse can be thought of as some kind of information which is stored in the synapse, right? So you can think of a strong synapse as representing number 1, and a weak synapse as representing number 0, right? You can think of that quantity itself as some kind of information which is stored in the synapse. In fact, there is the current theory in neuroscience is that all the information that we store in the brain is stored in the form of these synaptic strengths. Because brain is a large network of neurons, and neurons are connected by synapses, and synapses have some strength, right? You can associate some number to the strength, let's say W. So the whole pattern of these numbers, the W's, right, represents all the information that is stored in the brain. This is the current thinking in neuroscience. It's one of the fundamental tenets of modern neuroscience. That information is stored in the form of connection strengths between neurons. Okay, so we'll come back to this idea more and more in data classes. So now one of the most commonly found excitatory neurotransmitter is glutamate, and it has many receptors. And the neurotransmitter to receptor relationship is not one-to-one. For a given neurotransmitter, you can have multiple receptors. For example, for glutamate, there are 3 major receptor classes called AMPA, NMDA, and kainate. And the channel that is associated with this, so when the receptor and when the neurotransmitter receptor when they bind, the channel that opens is a sodium channel typically, right? For glutamate, and for GABA, which is a most commonly found inhibitory neurotransmitter, right? GABA stands for gamma aminobutyric acid. So the receptors, so there are 2 types, GABA A and GABA B, and the channel which opens because of that is a chloride channel, which is chloride is a negative ion, so when it flows from outside to inside. and therefore it has a tendency to reduce the membrane voltage. So now we'll present a very simple model of the synapse. So in the synapse you have two sides, right? You have the presynaptic side and the postsynaptic side. So if you want to model, you can have models of presynaptic side and postsynaptic side. That means there are lots of models of how when the action potential comes to the presynaptic side, how the calcium channels open and how calcium rushes in, and how that breaks the bonds of the vesicles, and how because of that the vesicles move. And there are also different pools of vesicles. There are those which are ready to go, right, which are loaded as though like a torpedo in a submarine. They are ready to go and bind the membrane and release their contents. Then there are slightly another pool of vesicles which are in the back end, right? These are called reserve pool. So when the boton quickly uh, consumes or exhausts all its vesicles, then the vesicles in the reserve pool come here and then try to fill up and replenish that gap. So lots of stuff that happens on the presynaptic terminal itself, and there's a lot of modeling effort on all that. So strictly speaking, a model of neurotransmission should include all that. But in this class, I'll only focus on what happens on the postsynaptic side. I'm not going to talk about how to model the diffusion of neurotransmitter molecules inside synaptic cleft, all that. No, my focus is completely on this. When a neurotransmitter binds with a receptor here, right? So let's say this is a neurotransmitter molecule that will open the channel and introduce some current, right? And opening channel means increasing its conductance. Okay, so the conductance increases briefly as long as the neurotransmitter is available. After that, it comes back to be its condition before. So how do you model that? That's what I'm modeling. With the receptor, the conductance of the corresponding ion channel briefly increases and then drops back. Right, that's a very small value. I'll give you this value later. So this brief increase in conductance and its return back to zero is modeled by this expression, A into T into e power minus T by Tp. So this function looks something like this. So at t equal to 0, this function is 0, obviously, right? So it goes to some peak value at t equal to Tp and falls off. Okay, so I'll call this G-syn, which stands for the conductance of the synaptic channel. That is the channels which participate in neurotransmission in the synapse, right? How does the conductance of these channels vary as a function of neurotransmitter? And note the neurotransmitter is released in the form of small packets, because each vesicle has a few thousand molecules of neurotransmitter. So when a vesicle releases its contents into the cleft, right, there's a burst of neurotransmitter released, and that will stay around in the cleft for some time, and after that they'll disengage, and they are even broken up by other molecular players in the synaptic cleft, and they're removed basically. The transmitter molecules are removed, right? Otherwise, it doesn't make any sense. The synapse is only meaningful. It serves a purpose only when it sends a signal at a given time in a given context. The signal is constantly on. If it gets stuck, then it's useless, right? So you have to have active mechanisms which remove the neurotransmitter molecules after they bind with the ion channels and convey their signal. So that is modeled by this function A into T into e power minus T by T. So the postsynaptic membrane, right, is you have the synaptic channels, right, where the neurotransmitter molecule binds. Okay, and this will allow current, right, and that's what causes the PSP. And then you have other channels in other parts of the postsynaptic terminal. We'll assume that these are passive. Okay, because I'm looking at the very simple model of the postsynaptic membrane. And also, this is a reasonable assumption because we said that typically there are no voltage dependent channels on the dendritic side, and this is dendritic side. Okay, so we'll assume that these channels are passive. Now, there's always the membrane itself, which is the capacitor. So basically, a minimal model of the postsynaptic membrane, which also captures the neurotransmission event, should have three components, which is the synaptic channel, right, with its varying conductance. This conductance is varying as a function of neurotransmission. Then that will have its own ESIN, right? So there's a battery in series with it. Then there's a capacitance of the membrane itself. Then the third branch is all other channels. Since it's a passive cable, all the channels are passive channels, leakage channels. So I can combine all of them into one branch. And so the resistance, I'm using the resistance R here, instead of conductance. And the battery of that is Vrest because under normal resting conditions, the synaptic channels are not active, they're closed, right, because there's no neurotransmitter. So therefore, the resting potential of the membrane is simply is some, let's say it's some value Vrest, right? So therefore, all the leakage channels, the battery of them is Vrest. So this is a minimal model of the postsynaptic membrane. Okay. Now, let us write down the first equation for this circuit. How do you times Vm, so this is Vm minus Esin times Gsin plus Vm minus Vrest, right, time by R. So this is 0. So this is a basic equation of the circuit. That's what we have. Now let us define a new variable, small v, which is equal to Vm minus Vrest. So what does the small v tell you? It is the deviation of the membrane voltage from the Vrest. Because if you look at EPSP and IPSP, in case of EPSP, you have a positive deviation. In case of IPSP, you have a negative deviation. So what is this deviation from? It's a deviation from the resting potential. So this is Vrest, this value. So this voltage is either it goes above Vrest or below Vrest. So it makes more sense to define a new variable which represents a deviation of the membrane voltage from Vrest. So that if that variable is positive, we call it EPSP. If that variable is negative, we call it IPSP. So therefore, we define this new variable small v, which is equal to Vm minus Vrest. And now write down the equation, original equation, in terms of this new quantity. So if you do that, if you plug this into this equation, you get C b small v by dt plus Gsin times small v plus Vrest minus Esin plus small v by R. So okay, so you get to this equation. So now let us see. So sorry, we are running out of time. Let us see in tomorrow's class. Under what conditions you see a positive wave of this small v or a negative wave of this small v. Okay, let us stop there. You have any questions? Hello, any questions? Okay, then. Yes, somebody. Okay, no questions. Let's meet tomorrow.
So, any news on mid-semester exam?
Yeah, Sandeep, we thought of October 8th, right?
Yes, sir. October 8th.
So because you have vacation from October 15th to 20th, so we want to finish it like sort of a week before that.
Okay,
All
sir.
right.
Thank you.